2 more minutes. Is that the whole class? I'm not quite sure.
Oh, you mean like how many people will be coming today?
Yeah, normally. I don't know. Yeah.
What are you guys doing?
There's like some people missing.
Okay, never mind. So,
Yeah, we're good. I mean, just a few. What did you base your project on? Okay. Okay, K was it a K?
It's a big data challenge that's sponsored by the company.
Okay.
Chinese company, so it's
cool. So let's start, right? So we're going to introduce TensorFlow. I mean, first of all, I'd like to make a compare of the recent state-of-the-art machine learning toolkits, and then I'll give a brief introduction of TensorFlow, and then I'll show some demos in iConsume notebook, including the basic operations and how to store the model and plot the models, and then I will introduce a visualization toolbox. So as we can see, there's a table for most recent used, most often used toolbox here. Siano is like the grandfather for all the other toolboxes, and the TensorFlow is here, and the author just highly recommend based on the table. For Torch, they have a new version of PyTorch released early this year, in January, 3 weeks before TensorFlow 1.0. So I would like to claim that it's not quite fair for the PyTorch because it's also a potential game-changing toolbox. So personally, I prefer this two. And the cafe is a kind of a old school fashion, and the main contributor are the code developer in TensorFlow now. So maybe we can skip this one. And MXNet is developed by the CMU guys. And currently it supports Amazon cloud space, so it's another a potential good candidate for cloud-based distributed machine learning. But currently this area is still dominated by TensorFlow and by the CNTK. This is the MSR Microsoft Research version of the because. As we all know, the Microsoft Research has some recent development in the called Inception. It's for the computer vision, image analysis, and both CNTK and TensorFlow have the most recent version of the Inception. It's Inception version 3, I guess. So based on their paper, the performance of some specific networks are better in the CNTK platform. So yeah, if you want to dig into some specific task, you might consider that also. And here's which is popular. So on the GitHub. So it's the contributors and folks and stars of this a state-of-the-art data set. toolkits, and TensorFlow is currently dominating. So I think it's a good start to like have a quick glimpse of TensorFlow first. So here we go. So let's get some intuition first. So what is TensorFlow? Why we call it TensorFlow? Basically, it forms of two words, tensor and flow. And tensor is basically a multidimensional array. It's let's see. The most data structure we use in the scikit-learn is NumPy array. NumPy array is a kind of a high-dimensional array. TensorFlow is just another name for this kind of a data structure. It's nothing fancy. And flow, as we can see in the graph theory, flow refers to the how the nodes connect and how can we navigate from one node to another. And here, the nodes are the operations. So before we get into the details, I'd like to show a short video.
Oh, the drawing board behind you. This thing is a knob or something.
There's a dial for the volume.
It's already on, I guess. No, never mind. Sorry about that. Just 1 second.
Okay.
Deep learning is this branch of machine learning loosely inspired by how the brain works. We have had experience building software for deep learning over the last few years.
Although it was initially a research project, we've since collaborated with about 50 different teams at Google and deployed these systems in real products across a really wide spectrum of areas. Today, it's used heavily in our
That's weird. Let's try again.
models are able to, they're really powerful at doing various kinds of perceptual and language understanding tasks. These models are able to actually make it so computers can actually see and are actually able to understand what is in an image when you're looking at it, what is in a short video clip. And that enables all kinds of powerful product features.
Machine learning is the secret sauce for the products of tomorrow. It no longer makes sense to have separate tools for researchers of machine learning and people who are developing real products. There should really be one set of tools that researchers can use to try out their crazy ideas, and if those ideas work, they can move them directly into products without having to rewrite code.
On the research side, the goal is to bring new understanding to existing problems, advance the state of the art on existing problems, understand new problems that weren't considered before. And on the engineering side, the goal is to take those insights from the research community and use them to enable products and product features that wouldn't have been possible before.
Part of the point of TensorFlow is to allow collaboration and communication between researchers. It allows a researcher in one location to develop an idea and explore it, and then just send code that someone else can use on the other side of the world.
We are making it a lot easier for humans to be able to use the devices around them. We think having this as an open source tool really helps that and speeds that effort up. So we expect developers to be able to do a lot more than they can do today.
We think we have the best machine learning infrastructure in the world, and we have the opportunity to share that, and that's what we want to do here.
Right, that's it. So let's come back to our theory. So based on the graph theory, so we can illustrate our logic of the program as a rectangle graph. So for each age, it is the tensor. So in that way, the data flows through the channels, and the nodes are the operations, including the constants, variables, and the computation debug or control flow. So here is a quick question. So if we have a loop, how can we get a DAG? So anybody have any ideas? So the tricky part I just mentioned that. So based on the traditional the graph model of the program, so if we have a loop, we illustrate as a we have cycles in between our graph. So why it's a kind of a there is no circle. So anybody? Alright, so the tricky part is the age. Previously, it's just the link of your logics, and for now, it's the flow of the data. So why we call it flow? So in the loop, the data kind of get updated every single step. So in that case, it's not the same. So have we ever talked about the feed-forward neural nets and the unfold that through time, right? So back propagation through time. We talked about that. It's the same idea, right? So the same structure just unfold into a more advanced network. Where's the graph? Okay, never mind. So I think it's a good timing to introduce TensorFlow because they just released the new industrial level libraries. Previously, 2 months ago, it was more like a demo toy. So for now, it's more flexible and they have better communication with other communities. And they are going to, the good thing I want to emphasize that they have, for now they have layers. Previously we just manually define our own data structure, the network structure. So in this way, they can automize the code, the code is as a graph, right? They can automize this graph automatically. So that's a good thing. Right? So what I want to emphasize in this slide is that, as we all know, Keras is another kind of infrastructure for machine learning. They support Ciano for quite a long time, and they have a fancy high-level APIs, and it's kind of user-friendly for the beginners. And if we don't need to tune in the hyperparameters or modify the details in the networks, so in that case we can just use something like Keras or Lasagna sort of things. So TensorFlow might be another standard API for Keras, and I think we will see actually. So here's a quick sample for TensorFlow. So we can see that this is an example in their official website. Each box is an operation, and we call it node. This is as we illustrate, the TensorFlow is the nodes are the operations and the age are the data flows. So in this case, have we already talked about the convolutional neural network in class? No? Not really. Okay. Okay, sure. So if you want to look into the details, you can check that link. And basically we have 3 types of layers. Yeah, the convolution layer is like the computational method. It's just we just apply a filter on the original image, and then we can get a domain transfer, domain adaptation, some kind of tricks. And then max pooling is kind of we select the local max in a specific region and downsample the original image into a subspace. And I think this idea is similar to the inhibitory neurons in our brain science, but it's not that stable because in that case we are basically solving differential equations, but in this case we are just no-brainer to choose the local max, but it's also the same idea. So that the drop-off is a kind of a fancy layer to speed up your training and make the convergence more stable. And we'll get to the details if we have some tasks like this. But this is a kind of a visual cue for what TensorFlow should look like. So okay, this side is some activation functions. I think we've already talked that in class, right? No.
Transfer function?
Activation function. Yes. So what is that? Give me a definition. Thanks. Or just some intuition where you're understanding.
So it's we transform the output of some node into some range that we want. We shape the output of the node in the neural networks.
Yes. Yeah, you got an idea. Basically, I mean, for the artificial neural networks, we are mimicking our, real neurons in our brain, but we just simplify that. So we need to find a way to decide if the neuron fire or not, right? So in that case, previously there was a step function, but it was too strict, and we come up with the ReLU, and after that there are ELU, or the SIG mode is a good start. Yeah. So ReLU is a kind of a most recently developed techniques, and it's you can see that it's computationally inexpensive. So yeah, currently it's we apply the activation function in between the layers. So in that case, we can transfer the data in that way. Alright, this is the Inception version 3 I just mentioned, and this is the most powerful network for now for the speech. For visual and audio recognition, and basically, so we have already covered the feed-forward neural networks, right? So basically, they have for the feed-forward neural networks, each layer just
Feed-forward neural networks is recurrent networks?
Not exactly the same, but yeah. Let's go back to the basic stuff. So the feed-forward neural networks is that each layer just receive the data from previous layer and output to the next layer, right? So recurrent neural networks is not exactly the same, right? So there's a loop, right? So but for this one, let's forget about the back loop for a moment. But the thing is that they will gather the input from the previous 2 or previous 8 layers. So in that way, it maintains a kind of global understanding, because previously the basic deep feed-forward neural networks are each layer is a representation of like our how to say that? It's more like a feature selection strategy, right? So the deeper the neural networks and the data, and I mean the visualization of the data become more abstract. So actually we lost a lot of information in between. So in this way we can just keep it's more like a long-term memory, but it's not performed in the same way. So this is the basic idea of this line of research. So as I mentioned before, the TensorFlow just released version 1.0, and they set up a keynote last month, and this is the link of that series of videos. And I don't know if we have time, but here's the shortest one. It's a case study. So would you like to watch that, or we can skip? Okay, let's go for it.
Hi everyone, so I'm Lily. I work on our medical imaging team in Brain, and in a previous life I was a doctor, and I've been repurposed as a product manager at Google. So one of the projects that we've been working on in our group is using deep learning for retinal imaging. In particular, we are looking at a disease called diabetic retinopathy. So that's, other than a mouthful, it's actually also the fastest growing cause of blindness in the world. And it's because this is a complication of diabetes. And diabetes, there are 415 million people in the world with diabetes, and each one of them is at risk for going blind due to what we call DR, or diabetic retinopathy. The key to preventing blindness is regular screening. So every guideline sort of worldwide recommends about once a year screening. And it's because this is pretty asymptomatic until you get to a point where there's irreversible vision loss. And at that point it's a little too late to intervene. And so this is done by taking a picture using a specialized camera of the back of the eye through your pupil. And then a doctor grades these images. We look for these little hemorrhages and little spots on the image, and we grade them on a sort of 5-class scale from no disease to the end stage, which is sort of proliferative DR. In many places in the world, including in India, where sort of our story originated, there are just simply not enough doctors to do this task. So in India, there's a shortage of 127,000 eye doctors. And because of this and other sort of systematic issues, about half of people actually suffer vision loss before they're even diagnosed. And so for something that's completely preventable, this is sort of unacceptable. And here is a picture of some of the people who are waiting in line to get screened. So even if you get to a place where there is screening, there's a long wait, there's long turnaround time. And so a lot of people end up being lost to care. The other issue is that even when available, doctors are surprisingly variable. So here in this graph, each color represents a different class of the category of disease, and each row is a patient image, that fundus image. And each column represents an ophthalmologist. These are US board certified ophthalmologists, and we had given them this sort of test set when we were kind of trying to attack this problem to see what the grades were for each of them. And as you can see, when there's no disease, there's pretty good agreement. There's one person who thinks otherwise, but everyone consensus is there. And then of course you look at the end stage when there's sort of proliferative disease, there's good agreement there too. But in between, there's actually a lot of variability and disagreement about where this should actually fit, even though there are pretty well-known guidelines. And it's because human beings in general just aren't super great at at being very precise about what we see in that image. And of course, you can see the two highlighted rows there in black. These images got every grade in the book, right? So depending on who you saw, your management would be kind of different. So, a little bit more about that later. So where we thought we could help was, let's train a model. And so we actually built a labeling tool. We started off with 130,000 images, and we've gotten much more since then. And we hired an army of ophthalmologists to help us label. From our 54 ophthalmologists, we got 880,000 diagnoses for these images, and you can see from the previous slide why we did that, because sometimes it took up to 7 reads to get something consistent. Then what we did after we got this data cleaned up and labeled, we kind of used our trusty dusty inception network that works for a lot of image recognition tasks, from cats to puppies to melanoma and now to DR.
So this is the convolutional neural net we just talked about. So but they use a much deeper version.
Trained it to detect sort of these 5 class predictions, but we also asked it to predict, sort of housekeeping things that may be important for a clinician to know, whether or not this image is of sufficient quality for grading, whether or not this is a left or right eye, sometimes we get confused, and also the field of view, which is what part of the retina you're actually seeing. And then we built a front end to this. I'm going to try a demo here. This is literally what I call a toaster. We try to drag and drop something.
So this part is not quite related to...
And are able to tell you that different type of mean, moderate, and severe. It's like, a case-by-case basis. But then, I kind of showed you how it works, a case-by-case basis. But then, how does it work sort of over a lot of images? Well, here we actually published and shared sort of how we did this work in the Journal of the American Medical Association. This is one of the tests or the validation sets that we use. The model was not trained or tested on this previously. And out of 9,963 images, we actually we predicted whether or not it had referable disease. So the y-axis is sensitivity, the x-axis is 1 minus specificity, and our algorithm and the 2 black dots, if you can actually see it, is in black. That's our algorithm, and then the little colored dots are US board certified ophthalmologists. And up and to the left is good, and you can see that essentially that we're very close to most of the ophthalmologists in terms of performance. And in fact, if you look at our F-score and you compare the algorithm's F-score to that of the median ophthalmologist, we're sort of in the middle of the pack. And one of the reasons we also decided to publish in JAMA was because we believe that engaging the medical community is really important to get these technologies out into the hands of the people who could actually use them. And so it was actually quite well received. You can see some quotes from real doctors about our work, and so we're really excited about that. So how did TensorFlow help us? Well. Every step of the way, I think, it helped us really start with quick prototyping, right? So we had starter architecture, pre-trained models, and we actually were able to try out different sort of variations of neural networks. And we actually found, we literally found that Inception V3 at this point worked the best. But we could try out things very quickly, and we also pre-trained. So we actually pre-trained on the classic ImageNet, and we found there was a boost in performance there. So it also helped us to experiment at scale. So GPU support and fast training. This allows us to run all these different experiments, different sort of labeling. If we had new labels or different labels, it kind of helped us do that. And finally, what I think is really important is that it really allowed our team to reinvest sort of the efforts. So the blocker was no longer in machine learning and in training, right? That's always been that's been hard to do. And if you look at what we did here, we actually applied very straightforward ML techniques here. What was the magic sauce was actually finding the right problem, getting the data, getting agreement about what was in the image, and then we were able to use sort of this package, these tools that were able to sort of allow us to train the models that actually performed really, really well. And that also then allows our team to focus on validating the algorithm and figure out ways to deploying it into healthcare systems, which in itself is a huge challenge. So what's next for us? We train a model, it works really well. And now we need to actually clinically validate it. We've been working with 2 hospitals in India, Aravind and Sankara. So what's next for us?
So what I want to show is right here in this box. So for most of you guys, I just want you get some inspiration from this kind of applications, because some of you are going to get some clinical data set. And basically, TensorFlow just save the pain of the training the model, because they have some pre-trained models. And in that case, you can just reassign the labels and then get your predictions. So it's already like, these pre-trained models are like, for Microsoft, they trained that for 2 years on their super servers. So yeah, so you get a like kind of a high standard starter point. So the only thing you need to worry about is how to like pre-processing your data and how to validate your model. Yeah. All right. So TensorFlow itself has a like very good formatted online tutorial, and I find another tutorial in like GitHub. So in the rest of the class, I will introduce some of the samples from that folder. So basically, you can find that it's a kind of a popular repository in this society, and it's updated recently. So I will start from like introduction and cover some utilities. And since I think most of you guys are going to like run the code on your laptop, so I'm not going to talk about the GPU enabled. So yeah, never mind. But yeah, you can definitely try it out. So just a quick question: how many guys are going to like use Mac as a platform? Okay. So other guys, are you going to use Linux or Windows?
Linux.
Linux. Okay. Okay.
You're
That's
going to use Windows?
It's gonna be fun.
Okay.
all right. So the issue that is that
I just couldn't install it.
yeah, if you want to use Windows, I highly recommend to use this. Right. VirtualBox. Yeah. So yeah. So basically, you get a like a Linux environment. So yeah, but for Mac users, it's much easier. So since we just have one student going to use this VirtualBox, so I will skip the like installation part, and I will just show a Linux environment. But for Mac, it's exactly the same. So. A little bit small, right? Let's see what I can do. So for this task, I'm still going to use avocado. So the first step is what? So do you guys remember how to enable avocado? Anaconda.
Just contact.
Source activate.
Yeah, the
That's
source
right.
activate. Yeah.
Uh-huh.
So I build a folder. Okay. So we're going to use my Python notebook. I will talk about this later. Yeah, actually, have we already covered the Tisney in class? No. So you guys know. So what kind of techniques are you going to use for dimension reduction? PCA, yeah, yes. So Tisney is like a most recent alternative model for the dimension reduction, and it's kind of get the state-of-the-art performance. So one good thing about the TensorFlow 0.0 is that they just modify their visualization toolbox. Previously, for the TensorBot, they just include the like the graph output, something like what we showed in the previous slides. And for now, they have a kind of a powerful visualization building function called like embedding visualization, and they use both Tisney and PCA. So I think I can show you. This. So I think this short video give you a better understanding of what it looks like. So basically, it's the Minister data set. It's the same digit data, not the same, but it's a similar data set as we used in homework 1. So yeah, you can see that we have a kind of a decent tools to visualize the distribution of these digits in the 3D data, 3D space, and it's also support 2D. So I mean, in paper or something you cannot plot it in a video. So in that way, it's a kind of a good tools for publication. So and actually the usage of this fancy tool is quite simple. We will cover it in the very end. So if we have time, yeah. But I recommend to have a look at it. And this is the main website of this guy. He's the first author of the Tisney, and they have some recent updates, some accelerating techniques. And in that case, we can perform it. By the way, the Tisney is much more slower than PCA, so yeah, if you want to try on a huge data set, you may want to get prepared. So, and for the their new approach is, I mean, the time complexity is more feasible. It's like O(n) squared, something like that. So, but as you can see, it's not ideal. But yeah, but the performance is great. All right. start from TensorFlow first, and then we'll go back to the TC. And as we can see, first of all, we need to import the library, and it's a straightforward. It's called TensorFlow. We can import it as TF, and then as we talk about, the nodes are, the variables are the nodes in the graph, and it contains the constant variable like static variables and dynamic variables and other stuff. And this is the major part of TensorFlow. Basically, the major difference between TensorFlow and scikit-learn is that the scikit-learn is just kind of a top-down logic. So you can just define your variables and define your model and make the configuration and then train your model and then validate your model and then get plots. So for TensorFlow, it's a kind of a encapsulation into like a section. For the section, it's like a block, and inside this block, we can execute our program. But we need to make the configuration outside of the box. So this is a kind of a basic configuration, and we use like string constant as input, and then we can and then we decide define the session, and then we can run the session. Oh, and by the way, it's always a good habit to clean it up by ourselves. So always close and release the resource. Yeah. So that's it. TensorFlow is just that simple. I mean, logically, right? So let's talk about some basic operations. First of all, we can, as we can see, TensorFlow is not just a platform for deep learning. It also supports like basic machine learning methodologies, and also by definition, TensorFlow is supposed to be like non-P array. Non-P style library. So in that case, it supports basic matrix and like tensor operations. So the most basic one are like addition and multiply, right? So here's a quick sample. So by the way, I don't recommend to always write in this way, because it's better to define your session and run the whole session in a block, and then in that way it's get the best performance. And I mean, for their compilers, they can just modify that and optimize that into a better graph. So in that case, it will be better. So if you just run the session separately, they don't treat them as a one-shot. Yeah. So this is the basic operations and the result. And then we come to the data structure. In TensorFlow, there's a function called, there's a method called the placeholder. Basically, it's predefined the data structure, the size of the data structure. It can be 1D or multiple dimension. So in that case, it's like 1D and with a data type of int 16. And as you can see, we can modify the basic operations into a more standard way. So in that case, we can use built-in functions called add and multiply. So in this way, as we are going to introduce in the later sessions, all the other advanced functions are also executed in this way. So it's a kind of a uniform form, like a universal form for the TF operations. And I highly recommend to use with inside of Python. It can manage your resource automatically. So so in this session we can run different runs, but yeah. And as we just mentioned, tensor is like a matrix or high-dimensional multi-array. So the matrix operations are the basic operations inside of this architecture. So instead of use multiply, we use a matrix multiply, and in that we can get it like multiply as a matrix. And that's will be all for the basic operations. Do you have any idea so far? Any questions so far? Okay, let's move on. Okay, since we are going to dealing with machine learning applications, so we are not going to manually input our data set. So the first step is to load the data set, right? So the good stuff about TensorFlow is that they have much more like advanced data set in their own distribution, in this distribution. And in scikit-learn, we have the similar digit of the minutes, but it's smaller in terms of size and in terms of the data set itself. So here we have the original minutes data set, and let's cover it one line by line. So you can import the data from the input data. It contains several fancy data sets, and then you can load your data into your environment. And here's one thing I need to emphasize, that one hot label. Basically, if we have like 10 classes, we don't name it as a class 0 to 9. We name this as for digit 0, we name it as 1000, right? In that way, it's a kind of a vector of 10 digits. Each digit is a binary label for that specific position. So in this way, we have a uniform representation of the labels. In that way, we have it's also a multi-array, and in that case, it can speed up the training process and have a unique. And I think for most tasks, we should turn it on for the one hot flag. And then we come up to the hyperparameters. So in scikit-learn, we don't have quite a lot of parameters in terms of the model, because as we can see, we cannot manually decide when should we stop the training process, right? Because it always got a converged result, and in practically speaking, it's not always the case, because sometimes we just cannot get a global optimal result, or in the end it will be frustrating and we just need to stop at a specific point. So in this way we should design the epoch. Where's the epoch? Okay, not here. Because it's just a learning, loading the data. Oh, sorry, I should introduce that in the second, the third demo. Okay, never mind. So the learning rate is how can we update the model? So in what step should we update the model? So here it's a fixed learning rate, but for most advanced pre-trained models, it's a kind of a dynamic learning rate. At first, it should be large enough, so it can get to the the sweet point fast, and then it will be small enough to get converged. So batch size is one good feature. One important parameters in the training process, because it represents how many data should we fit into the network. At a time. So if we just have a small data set like the previous one, we can just use one batch, right? Put them all together into the, and we can get the best optimization result, because it's like the most accurate version. And in terms of SG, stochastic gradient descent, because the batch size is to just control how we get the gradient descent. So if we use a larger batch size, it will influence the memory size for the training process. And as we can see, the memory is a kind of a limited resource. We need to control that into a reasonable region. So in this training, 100 will be fine, but yeah, actually we can try a little bit larger. So, yeah. So this is the basic model called MLP. So we can see that we just define the size in the configuration section, and then just input the designed layers into the network structure. And the weights and biases are how can we just add up that neurons, the value of the neuron output, and then plot into another layer. So basically each neuron has its own weights, and then we have a global bias for each layer. So if we don't have, the issue is that if we don't have a bias, it will be frustrating a lot, and then sometimes if we get a bad initialization, it won't learn anything if we just set all the bias at 0, and the other weights, yeah, you know what I mean, yeah.
Excuse me?
Yeah.
I noticed that the scikit-learn also provide the MLP.
Yeah.
So the quick question is,
right.
Why it is better, or why do we want to use
Yeah, because yes, for the scikit-learn, the MLP is more like a black box. You cannot, for
every parameter in the
yeah.
except node.
Yes, as you can see here, we can manually define our the structure of the layers,
Okay.
and we can define the activation functions, and For this model, that will all. But yeah, but for more complex models, we can define some more stuff. And yes, for scikit-learn, I would say that for this kind of simple models, it won't be too much different.
Okay.
Yeah.
Because this, we can customize it.
Right. And the good stuff is that when you customize that, you can like get the intermediate output and plot each layer into like visualization toolboxes, and we can get a better understanding what is going on in between. So yeah. So that part is all about the configuration, and this is the initialization I just talked about. So here is a good stuff for TensorFlow, because we can save the data for later use, and we can save and we can load the data we can load pre-trained models for other kind of inputs. Great. So as it shows here, it's just as simple as execute the session run for the image. And this is the epoch we talked about in the beginning. We can control the epochs to like manually decide when it's a stop point. This part is all we need to consider during the training loop. We just use the function called next batch, and then input the batch size, and we can just feed the data into the network, into the model recursively. So I will skip the optimizer part for this model. All right. Next part is not so important in this one. So as we have already loaded data, so it's also loaded. Okay, so kind of a better understanding of the data itself. Yeah, sure. So as we all know, the image, the digits in scikit-learn is like 8 plus 8, but for now it's 28 plus 28. It has a like better resolution, and it also has more samples. And actually, it's easier for us to train and test because they've already have their official separation, splitting for the training and test. So we can just conduct a cross-validation or something on the training set, and then use the holdout test set as a like make it comparable to others' work. Yeah. in terms of models, let's start with most basic one for classification. It's a logical regression. And here we're going to use the same data. Shall we go line by line? Okay. So the hyperparameter including the epochs, learning rate, batch size, and displays that. It's just about how to plot your data set to get a monitor of what is going on of your training process. And the placeholder is define the size of the input data and the labels. And this is the weight and the bias. It's exactly the same. And the prediction is like the softmax is always the output layer. It's exponential average of. The good stuff is that it can sum up to 1. So in that case, it makes sense in terms of prediction score. So it's always a good candidate for the output layer. And the cost function is the object function you want to optimize. And cross entropy is what we use here, and is also a popular candidate. And optimizer, we have already introduced the gradient descent, right? So here is a standard gradient descent, stochastic gradient optimizer, and we have some more advanced optimizers called Atom or something like that. It's a adaptive sort of gradient descent. And initialization, we can use this random initializer. And the whole structure is kind of exactly the same. Any questions so far? All right, so let's move on to kind of a complex network. Autoencoder is one of my favorite network. As basically, so we have talked about autoencoder in class, right? No? Not yet?
Not yet.
Okay, sure. So autoencoder is a kind of a special neural network. Is that the input layer and the final output layer are the same size, and in the middle we have a bottleneck layer, which has a very limited dimension, and in that way it's more like, in my personal understanding, it's more like our attention model, because our short-term memory is always limited. So we can just extract some essential part of the current environment, and then to get a better understanding of what is going on with this kind of information. So basically, most attention models nowadays are based on the short-term memories, and previously it's more like long-term memories. So in that case, I think autoencoder is one of the most natural neural network architectures lying there to illustrate this kind of attention behavior. So, and by the way, the autoencoder consists of two parts. The first part is the input layer to the bottom layer. It's called the encoder, and that means we just encode our like observation into like compressed data representation. And then another part is called a decoder, which start from the bottom layer to the up layer. So if we want to like get a like prediction, we just apply a softmax on the bottom layer to get the classification output. Okay. So here we have two hidden layers. I mean it's a symmetric. So we have two hidden layers in let's see. Two hidden layers in the encoder part and two hidden layers in the decoder part. So here we can see we use like another popular optimizer. It's probably the same to the salicylic acid gradient. It's called a roost mean square prop. But yeah, you can use both actually. It doesn't matter. I mean, it matters in terms of your data representation. You can try the best one and validate the model. I mean the optimizer based on your data set. And there's another session called interactive sessions. I don't recommend to use this in your own training process because it's more for verification, for visualization. So yeah, it's convenient for notebooks, but not for the real training. So any questions about this model? No? Okay.
Detected them pretty good. What's the output?
Hey, you guys are pretty awesome.
It's not one of them. But did pretty good.
Right. Did pretty good. Yeah. MLP. Shall we go to MLP? Maybe not. Okay. It's I should include it before the autoencoder because it's a kind of a antique stuff. You can see that the structure is pretty the same, right? Parameter like configuration and model configuration, and it's also the model configuration, and you can define the like this part is in this session, right? So we can define the objective function and the optimizer, and that's it. Model, object function, optimizer, and initialize. We also use the global initialization. But for some building advanced models, something like instruction verse 3, they have a special initialization. So yeah, you can load their previous data. So in that case, we can cover that if we have another lecture. No, I don't know. Yeah. and the training process is exactly the same. So we have finished the training part of in TensorFlow, and then we need to find a way to validate or to evaluate our model. And as we mentioned in previous class, one metric is the classification accuracy, and we also have F1 score confusion matrix, and we also have ROC, and on top of that, we can visualize the data set by something like PCA or t-SNE. So this is a good time to cover t-SNE first, and then we're going to cover the tensor notebook. TensorBroad. So we have already Stefan has introduced the Bayesian inference in class, and basically it's the t-SNE is trying to get a dimension deduction by implementing the KL divergency. So it's basically get the expectation of the exponentially rate. So yeah, you can get it into this function. And the Q is the observed distribution, and the P is the true distribution. And do you guys have any ideas about this? I hope so. Because it's similar to the Bayesian inference, right? So yeah, we can, and it's always the standard form to use a KR divergency because we cannot get the total diversity. It's not calculable. So in most cases, for the Bayesian inference and the variational inference, we just use the KL diversity. It has a strong restriction is that they have assumed the distribution. The sample distribution is a Gaussian. So yeah, it's not always the case, but yeah, if we have a large enough data set, some researchers claim that it should follow a Gaussian or a mixed Gaussian. Frankly speaking, I don't have too much experience in t-SNE in TensorFlow because previously they don't have that. They just released last month. So previously I just used t-SNE inside of scikit-learn, and it's not that slow, so it's acceptable. So, but since TensorFlow has already, officially supported this kind of feature, I think it's a good time to transfer to their platform. In that case, we can just, because we have already said that we can save and recover the models and each layers, and in that case, we can easily just plot out the tensors instead of doing the data format transforming, something like that. So this is the iris data set we talked in last lecture. So basically there are 3 classes, and there are 4 labels. So it's not that high dimensional space. So for t-SNE, it's always good to control the input size. I mean, it's not computationally efficient, so we should control the size of the input. If we don't control the size, it might not get it might get some weird performance. So the upper limit is about 50. Yeah. So that's what I want to show here. It's like 2D embedding of the Disney on the Minnesota data set. So for next homework, I guess it's good to get a kind of a similar visualization, and it won't be required, but I think it's a extra point. I would say that. And this is a quick tutorial for the tensor board. That's what you need to do here. You've already trained your model, and you get your log files, and you just input your log file into the this kind of a platform. So you can just execute this command on just on your terminal, in your terminal. Right? And this is the application. This one included in the old version, but yeah, also this one. You can get a visualization of what is your current logic and what's the flow in the network, in the graph. But they didn't show the new stuff. But yeah, let's check from. That part called the visualization learning. You can get this part. Graph visualization. You can get the graph of your network, and the new feature is embedding visualization. And it's not hard coded. You can just modify the details, and you can use PCA or Disney, or customize your own distance measurement. Oh, one thing I need to emphasize about Disney is that it's a kind of a dimension reduction techniques, but it has its own limits, because we cannot fit in new data, because it's a kind of a this representation is optimized on the current data, so it's not support online learning. But for PCA, it's easier to retrain your model, but for Disney, I don't think it has this kind of feature. And since there's a limitation, there are some more recent papers to find a way to mapping the new data into the already plotted space. But my suggestion is that if you are going to use Disney as a visualization tool, you better train on your own. I mean on your whole data set, and then you get a better understanding. Because in that case, you can get if there are any outliers in your data set or something like that. So it's always a good start to realize each layer, or not. I mean, in terms of autoencoder, it's a sophisticated way to do that. But for other neural networks, like CNN or RN or LCM, it's not always feasible. Right. So much about it. I think that's pretty much. So in this tutorial, it's just nothing more than how to save your training session. Save your training process in a way. So that's all about the basic neural networks. So, any questions? Or any thing you want to know in the future? Maybe I can cover if I have another chance. Alright. So in that case, class dismissed.
Actually, class just starts, so we can go home and we have to go to this.
Alright.
So thank you, but but we're about to start. Right?
Well, I've been reading after this for tonight.
Yeah. Well, I'm going home and I'm going to start. First, I need to recover. I have a good GPU, and I wanted to install the Suda libraries.
Oh, so
and that completely exploded, so now I have to reinstall Linux.
Oh. So in that case, if you want to use GPU, you also need to use CUDN.
Yeah.
It's a kind of a licensed library.
Yeah.
So you need to. You already done that.
That's where my Linux went completely crazy. So now I'm reinstalling Linux.
Yeah,
and
sure.
going back to installing the CUDA libraries first.
Yeah.
6 weeks. 6 weeks.
And front.
I can help with that if you want to come on Wednesday.
Oh, maybe I'll come on Wednesday. Yeah.
So by the way, I will hold the office hour here on Wednesday during the class.
During the
time.
class.
So
Okay.
yeah, so I will try to release the grade for homework 3. The first homework tomorrow night
Okay.
or afternoon. So if you have any questions about the grading, Thursday is Wednesday is the only chance to
Ask.
negotiate.
Okay.
Did we get any information on if we'd be able to get like online storage credits?
What is that?
I know someone was asking if we can get online cloud access credits.
What, search credit?
What kind of a cloud access?
Or just like somewhere where we can dump all of our information online. That way.
Oh, can we use Blackboard, the discussion board? No? You mean the data?
Or the data for our projects.
So can we just use a Google Doc? Because it's unlimited for US student.
Oh, okay.
I guess.
I think she's asking about like AWS credits or Google
Oh,
Cloud.
I don't think we have the authority to add additional students. I don't know because, it's not a
No, it's just for
standard
like,
service for.
just like doing like processing in the cloud.
Because we are going to use like tiny data set.
Yeah,
for your
small.
project,
For
right?
project.
Yeah.
In that case, it's it's if you get that from some clinical institute, they might have their own.
Okay.
But
So just
they
ask.
also have some license to forbid us to upload them.
Okay. Okay. I'll ask.
I guess.
Okay, see you Wednesday.
Yeah. Right.
See you guys. Bye.